So the point in this video is to determine whether or not a particular schedule is serializable. We'd like to know that, hey, if I have this ordering of actions, does the end result look like as if we had just done all of one transaction and then all of another transaction and then all of another transaction? Does the interweaving look like a serial schedule? So the way that we do that is by looking at conflicts. So once again, we're trying to figure out the ordering of actions that we're allowed to do. And we want to avoid illegal scheduling of actions that cause conflict. We want to avoid things where the transactions are interfering with each other, that they're not isolated anymore. And so the way that we do that is by looking for conflicts. A conflict occurs if there is a pair of consecutive actions in the schedule such that if you change their order, then the behavior of at least one of the involved transactions will change. It means that if you change the order of these two actions, the result changes. And so in order to talk about conflicts, I'm even going to change to an even simpler notation than I had in the previous video because I just want to make this as condensed as possible. So if I say RI parentheses X, and this is a common notation for database notation, it means I'm trying to read on database element X in transaction I. So the I is the name of the transaction that this action is a part of. If I say WJ of Y, it means I'm trying to do a write operation on J that's on database element Y, which in this case, because X and Y are different, it means I'm reading from one element and writing to another. And the other bit of notation are what are called action pairs. So I'm going to just say one action, semicolon, another action. So for instance, in this action pair, I'm reading in transaction I from element X, and then I'm also reading from transaction J element Y. These are two different reads occurring on different transactions occurring to different elements. And so one thing that's important to note is if I'm reading from two different elements, from two different transactions, do those ever conflict? Does the order, if I do this one first or that one first, ever matter if I'm doing two reads on different parts of the database? No! Like if I read from the table students and I read from the table elements, does it matter if I read from elements first or students first? No, it doesn't. In fact, it doesn't even matter if they're the same element. If I'm reading from table students in one transaction and I'm reading from table students in another transaction, does it matter which transaction, which action goes first? No. So that's the sort of things we're checking for. Are there conflicts between two of the actions in an action pair? Okay, so two reads, never a problem. Reads can't change the database state, so there's no way for these two different actions to ever interact with each other. There's no way for one action to affect the result of another. Okay? However, there are a lot of other different types of action pairs we have to watch out about. For instance, hey, what if I read from one element, like I read from the table students, and I write to the table employees? Does that order matter? Does it matter if I read and write on different objects and transactions? The answer here is no. If I read from the table students first, I get the same result as if I read from the table students after. And the write, consequently, is not affected either. So this is never a conflict. If I read from one transaction and write in a different transaction to two different objects, I don't have to worry. All right, what about this? What if I write to the table students in one transaction and I write to the table employees in a different action? Will these ever conflict? No, right? Changing one element over here will not affect changing a separate element somewhere else, right? Which write comes first doesn't matter because one write will not affect the other. All right, what about this? What if I read from an element X and I write to an element Y in the same transaction? Is that a problem? This is. The order of actions within a transaction are fixed. You can't say, oh, I'm going to read from X and then write to Y and then change the order within a transaction. You're never allowed to change the sequence of actions within a transaction because the scheduler doesn't know like the logic of what's going on inside that transaction. Perhaps that read from X gives necessary data to inform what the write should be, or the write from Y changes the database in such a way that future reads may be influenced. You don't know that for sure. So the rule is you're never allowed to change the order of actions within a particular transaction. So actions always conflict within their same transaction. So if the transaction does action A, B, and C, every ordering in a serializable schedule must be A somewhere, then B somewhere, then C somewhere, but in that same order. What about this? What if I'm trying to write to the same object? Two different transactions trying to write to the same object. Do those conflict? Yes. Why? Because if I write, dog, I know if I add Josh to the table of students, and then I add Charles to the table of students in a different transaction, whether I added Josh first or Charles first ends up with a different database state. So if two different people are trying to write to the same thing, whichever one goes first has a different effect than the one that happens right. Whichever one goes first will then be overwritten by whichever one comes later. They're both trying to change the same thing. And order here matters. And if you assume that there is the no coincidence assumption, we assume that the two things being written, that transaction I and transaction J, are trying to write different things to database element X. Now, it could be just by chance that transaction I is trying to change Josh to give him a 4.0, and transaction J is trying to change Josh to give him a 4.0, and in which case they actually wouldn't conflict because they're trying to do the same thing. But in general, you can't make assumptions like that, so you always assume that there are no coincidences. Everybody is trying to change things in their own unique way. All right, what about this? What if I'm trying to read and write to the same object? This does matter. Why? Because if I read first, I get the old value, and then I write to it and change that value. But if I write first, I change that value, and when I read, I get the new value. So which action of these comes first will affect the result of that read. And so that is a conflict. It means that if you change the ordering of this pair, you get a different result than you got before. Okay, so let's talk about why we care about these conflicts. If we have two actions in different transactions, they don't conflict. Generally, two actions in different transactions don't conflict, which means you can reorder them however you want without any effect, unless they involve the same database element and at least one of them is a write. If you go through the previous rules and you figure out when are there conflicts, here is another way of saying those same rules. They have to be different transactions. They both involve the same database element. At least one of them is a write. All right, so let's talk again about schedules. If I have two schedules, they're called conflict equivalent if one can be transformed to the other by a series of non-conflicting swaps of adjacent actions. It means I can bubble an actions around and reorder them by doing little swaps. And it's called conflict equivalent if I can basically say this schedule can become this schedule if I do these little swaps. And because each of those little swaps doesn't matter if they don't cause conflicts. If they don't cause conflicts, I can always just swap those orders around. And so if I'm able to do non-conflicting swaps to take one schedule to another schedule, it means they basically do the same thing. And this is really important because we really care about is conflict serializable, which means if a schedule I can do these little non-conflicting swaps over, and if I can eventually turn it into a serializable schedule, it means that the original schedule is serializable. And once again, to emphasize, this is the important thing, all conflict serializable schedules, meaning I can do these conflict equivalent switches, and if I can generate a serializable schedule, then hey, the schedule that I had originally is serializable. I could have just ran that. I didn't have to do those little swaps. So to help reinforce what is conflict equivalent, and more specifically, what is conflict serializable, let's look at, here is a particular schedule. Now, once again, what is a schedule? It is a series of actions done by 0 or more transactions. So here we have two transactions, transaction 1 and transaction 2. And note, they work on different elements. So some of them are on element A, some of them are on element B. And is this a serial schedule? Do all of one transaction occur before all of the other? No, because I do 1, 1, 2, 2, 1, 1, 2, 2. This is an interweaved schedule. Okay? So I want to see if this is conflict serializable. So how do I do that? Well, I need to see, can I do conflict safe swaps and turn it eventually into a serializable schedule. So for instance, let's look at the action pair that I've denoted in red here. This is a transaction 2 trying to write to A and transaction 1 trying to read from B. Do these two actions conflict? No. They affect different objects, so they can't conflict with each other. So what I'm going to do is I'm going to swap these two. So I've swapped them, and now, see, now I swapped them. Now it's R1B, W2A. And now I say, hey, look at these two. Am I allowed to swap these two? Well, this one is reading from A, and this one's reading from B. Is there a conflict there? No, I'm reading from different objects. Go ahead and swap them. So I've swapped them, and I said, hey, this action pair, am I able to swap these two? Well, they're writing to different objects. So does the order here matter? No, I make that swap. Hey, do these matter? I'm reading from A and writing to B. Am I allowed to make this swap? Sure. And hey, look, I've converted this schedule into this schedule, and this schedule is a serial schedule. This is a serial schedule, which means that this original schedule and really every schedule in between are conflict serializable. I can do these sorts of swaps and eventually get to a schedule like this. All right. So once again, is this schedule conflict serializable? Yes, because there was a sequence of non-conflicting swaps that I could have done to make it serialized. Okay, so the big question you should be asking yourself is, how the hell did I know which of those swaps to do? And the correct answer here is, of course, magic. Okay, no, I'm just being silly here. The way that it goes is, what you can do is you can look for all pairs of conflicting actions in a schedule. And if you have any conflicting actions in a schedule, the rule is the transaction of those pairs must be in the same order in the eventual serial schedule. Because we can't rearrange the order of a conflict, like if an action number 3 here conflicts with action number 17 here, the rule is the transaction that does action 3 must be before the transaction that does action 17 over here, because there's no way for me to ever make the later transaction or the later action come before the other one, because I would have had to try to do a conflicting swap at some point. So I can determine, hey, find all of the conflicts and figure out, okay, wherever all the conflicts are, this must mean this transaction must occur here, and this transaction must occur here, and this transaction must occur here, and then I can look at how to make the swaps happen. And so we can figure out the necessary order of transactions in the serial schedule, in the schedule that we're trying to find, by looking at what's called precedence. So what precedence means is, if I have transaction 1, which here is just T_1, or T sub 1, T sub 1 takes precedence over transaction 2 in a schedule. The way that we write that is T sub 1 is less than T sub 2, meaning it has to come first. If there are actions, which we just denote A of 1 of transaction 1 and actions of A of transaction 2, such that A1, that A1 action is before A2, and A1 and A2 both involve the same database element, and at least one of A1 and A2 is a write action. Now, what is these two rules here? These are the rules for does A1 conflict with A2. That's just another way of saying the same thing. And now notice, these are the exact same conditions under which you're not allowed to swap the order of A1 and A2. So if A1 will appear before A2 in any conflict equivalent schedule to S, it means if A1 appears before A2 and they conflict with them, you better have a serial schedule where T1 happens before T2. All right. So what we can do now is we can draw what's called a precedence graph of all of the transactions in a given schedule S. And the way that we do this is we draw an arrow, an arc, from a given node to another node if one node takes precedence over the other. So let's imagine that I told you that T1 takes precedence over T2, that you looked and you found, oh, there's an action in T1 and there's an action in T2 that conflict with each other, and because action 1 from T1 comes before action 2 in T2, then T1 must come before T2. So the way I can draw that is I can draw a node for T1, a node for T2, and I can draw an arrow, an arc from T1 to T2. All right, let's say in this same schedule, there was also, you determined another pair of conflicting actions that denoted that T2 takes precedence over T3, so we need to add a T3 node, and we need to draw an arrow from T2 to T3. And let's say that we found an action that said, hey, T1 conflicts with T3, T1 must come before T3. We can draw another arc here. And what this means is that the possible conflict serializable schedule, the schedule that we're trying to turn our original schedule into, the serial schedule we're trying to confirm, must have T1 has to come first. It has to come before T2 and T3. And then you'd have to do T2 because you're not allowed to do T3 until T1 and T2 are passed. So this is, you're looking through the graph and you want to see, is there a way to get through the graph such that you fulfill all of the dependencies of each node before you go on to it. T1 has no dependency, so it can occur first. T2 has to come before T3, so the only possible ordering, the only possible serial schedule for this is doing T1 and then T2 and then T3. Alright, so let's go through an example where we calculate precedence. So here is another schedule. Here there are 3 transactions, and I've just colored each transaction to make them a little bit separate because often it's hard to read the 1, 2s, and 3s. So transaction 1 is blue, transaction 1 is blue, transaction 2 is red, transaction 3 is black here. But otherwise the color has no particular meaning. So I need to look for conflicts here. Are there any times when 2 actions from different transactions are writing to the same element or reading and writing to the same element? So let's look through where are the conflicts. And this is something that we'll do more examples of. This is something that you should come up and write your own schedules and see that you can identify conflicts. So there I'll denote all of them. So R2 here, R2A conflicts with W3A. Note, they're different transactions, 2 and 3. They're the same database element, A, and one of them at least is a write. So what this means is transaction 2 must take precedence over transaction 3. There's no way for me to ever swap the order of these 2 in this schedule. Okay, fair enough. Are there any more? Yeah, so R1B here conflicts with W2B over here. Once again, different transactions, same element, one of them is a write, which means transaction 1 has to occur before transaction 2. There's often many. Okay, so here I'm reading from A and writing to A and reading from A. One of them is a write, same database element, different transactions, conflict, T2 comes before T3. I also have W2A here, conflicts with W3A here, same database element, different transactions, at least one of them is a write. In this case, both of them are writes. Another conflict, another precedence. And we have, gosh, there's still more, I keep finding them. We have one right here for reading from B, and we're writing to B right here. Different transactions, same database element, one of them is a write, another precedence rule. And we have another one here, this guy and this guy. And now some of these are redundant, but the important thing is you need to check all possible conflicts because you need all possible information regarding precedence. And so now we can draw our precedence graph. So T2 takes precedence over T3. So I got T2 here, I got T3 here. I can draw the arc. Okay, T1 takes precedence over T2. T1 points at T2. And that covers all of the arcs here. And so now, now that we have our precedence graph, we can actually look at it and determine, is there a way to satisfy this ordering in a serialized schedule? And here it's pretty easy to see. I need to do T1, then T2, and then T3. All right? And the important thing to note here is, how did I know I needed to do T1 to T2 to 3? Because T1 didn't have anybody pointing at it, so it is happy to go first. Then T2 was satisfied because at least T1 pointed at it, and then T3 here was satisfied because T2 pointed at it. And so T1, T2, T3, that is the conflict serializable schedule's serial schedule. This is equivalent to if I just had done all the transaction 1's actions first, then all of the transaction 2's, and all of the transaction 3's, and you can go through the step and do the rotations to make that happen. Okay, so the important thing to note here is that all conflict serializable schedules will have an acyclic precedence graph. If the graph is acyclic, it means there is some way to walk through the graph in a legal manner. And so it means that there is a topological ordering of the nodes. Now, if you don't know what topological ordering means, it basically means, is there a way to walk through the graph such that you always fulfill the dependencies, you always fulfill all of the nodes pointing at it first. However, if there are cycles in the graph, T1 points to T2, which points to T3, which points to T1. If there are cycles, there's no way to come up with a reasonable ordering of the transactions, because you can't do T1 until you've done T3, and you can't do T2 until you've done T1, and you can't do T3 until you've done T2. There's no way to order the graph. So if you ever have a cycle in your precedence graph, that is the signal for, hey, this schedule is not conflict serializable. All right, so multiple choice question time. Is this precedence graph conflict serializable? All right, so the question you should be asking yourself when you look at this are there any cycles here? Are there any cycles in this graph? No. I never have a T1 points to T2, points to T3, points to T1. No, I can, there's no loops, there's no paths in which for me to go around. Now there are edges that can form like, looks like loops, but the direction here matters. If I do T1 and then T2 and then T3, that's fine. And then I can also do T4, I gotta do T1, T2, and then T4 before T3. And there's actually a couple different orderings here. In fact, can you tell me which of these serializations are equivalent to this precedence graph? Meaning, which of these are legal orderings according to this precedence graph? All right, let's actually walk right through. So, am I able to do T1 first? Sure, T1 doesn't have anybody pointing at it. After doing T1, am I able to do T2? Sure, because the T1 has already been satisfied. After T2, am I able to do T3? No. Why not? Because T3 needs to have T4 come first. So if I do T1, T2, and then try to do T3, T4 will get upset. Okay, so the first one, no go. First one's wrong. Let's try the second one. I can do T1 first, sure. I can do T2 next. Can I do T4? Sure, it doesn't have any dependencies. And now after doing T1, T2, T3, can I do, T1, T2, T4, can I do T3? Yeah. Oh wait, what about this order? Can I do T4 first? Sure, T4 has nobody pointing at it. Then can I do T1? Sure, T1 has nobody pointing at it. Can I do T2? Sure, because it's the one guy pointing at it has been fulfilled. Now can I do T3? Sure. So actually, these two schedules here are both perfectly fine. Now there's other ones that I don't have here, but regardless, these two schedules would achieve the same effect according to this precedence graph.